We, the Indian Society of Heating, Refrigerating and Air Conditioning Engineers, ISHRE, stand tall in the Indian industry with over 10,000 professionals as members and almost an equal number of student members. Founded in 1981 and headquartered in Delhi, we operate from chapters and sub-chapters spread all over India, bringing our entire industry together. Individuals become members of our society according to their professional and academic standings. Our roadmap of the future looks very bright, with thousands of new members joining this technical society every year and bringing in a fresh outlook to our industry intelligence. ISHRE disseminates knowledge through its technical committees, which consists of some of the best minds of our industry. It publishes technical books, newsletters, and a prestigious journal, distributing the wealth of knowledge to all its members. Working with government departments, ISHRE helps formalize industry codes and standards. ISHRE promotes research by offering financial support to student members to carry out groundbreaking work in technology, systems and processes. Our educational wing, ISHRE Institute of Excellence, organizes training programs and workshops to help members enhance their skill sets. Our specially designed certification programs under ICP, that is, ISHRE Certified Professional, empower professionals to always be in step with the prevailing technology. Specially designed courses for technicians are offered to meet the ever-increasing demand for a skilled workforce. ISHRE organizes exhibitions, conferences, panel discussions, and product presentations throughout the country. We organize the industry's largest international exposition in South Asia, Acrex India, to showcase the cutting-edge technology, innovation, and provide a platform for closer interactions amongst the decision makers in the industry. The Acrex exhibition is now growing from HVAC&R show into BFA, Build Fair Alliance. This brings together several allied shows connected with the building services industry, all at one location. Our chapters organize several other popular events like AgriConf in Delhi, Raycon in Kolkata, Symposia in Mumbai, TechFest in Goa, and many more. We are committed to provide training and career guidance to our student members through seminars, lectures, quiz contests and site visits. A-Quest, a prestigious quiz competition organized by ISHRE to catalyze the transformation of the budding engineering professionals. ISHRE provides a platform to potential employers to select student members for careers in HVAC&R industry at the ISHRE Job Junction. Young minds are made aware of the need for saving power, clean air and sustainability. The K-12 initiative of ISHRE focuses attention on school students' development to inculcate a scientific fervor and help develop them into responsible citizens. Speedy information is imperative to keep moving forward in this hyper-connected digital age. Searcher, a specifically designed search engine, is now available, which allows access to a well-catalogued database on HVAC&R and building services industry with just a few clicks. ISHRE cooperates with various national and international bodies, industry, governments, academia, think tanks to promote the concept of sustainability, environmental protection and energy efficiency and conservation to enter and explore the universe of the Indian HVAC&R industry. Log on to ishray.in that unfolds a panorama of information. Let us engineer a sustainable future together through Ishray.
Good evening to all. Now, once again, welcome to all. And today's topic is learning about refrigerants, and that is given by Dr. Nilesh Purohit. He is PhD in mechanical engineering with specialization in thermal engineering. Is currently working as research and development engineer with Honeywell India. His primarily focus in on development of LGWP refrigerants for HVAC&R applications. He received his doctoral degree from BITS Pilani in 2018, ME degree in thermal engineering from MBM Engineering College in 2014, and his BE in mechanical engineering from Rajasthan Technical University. He has published more than 20 research papers in national and international journals and conferences. Welcome, sir.
Thank you very much. I welcome
No, sir,
all
start,
the
sir.
okay. I welcome all the participants and the students and the professionals. Most of them would be working in the industry, or some of the final year students, third year students, and some professors. And I'm very thankful that yeah, this opportunity has been passed over to me, and I will try to give an overview what actually refrigerant is and the related topics around the refrigerants.
Sir, share your screen,
So
sir.
yes, I'm just about to share my screen. Please, anybody can confirm that if my
Yes,
screen
sir.
is visible.
Yes, sir. Yes, sir. Visible.
Okay, perfect.
Now increase.
So
Okay,
yeah,
sir.
so okay, thanks. So what I have decided, I will go through my presentation, and whatever the questions and the doubts are, we can take that at the end of the presentation, and I will try to answer each and every question as far as I can. So I'm going to talk about refrigerants today. So basically, I would be starting very simply. What is a refrigerant? What are the types? How we can group the refrigerants? How we can designate the refrigerants? How we can classify them? How we can blend them to take the advantage of various available refrigerants? How we can detect the leaks from the system? And at the end, we're going to go in much details. That is very important, that what are the desirable properties, what we are looking for any refrigerant. And then we will look about the how the refrigerants have evolved and what is the futuristic roadmap of the refrigerants, where we are heading. And after finishing this, I will go and touch base on supermarket refrigeration, that is being very close to my research throughout my career. And we will see that how the supermarket refrigeration system architecture looks like, what are the different architectures which are used, and what as a student or as a professional, as a researcher, we can do to improve the performance as well as the environmental benefits. So this would be my agenda. This is very simple, and I would welcome each and every to ask any of the doubts even after this presentation. And also you can get my email and my contact details where you can touch base with me. So starting with refrigerants, it is a fluid for absorbing and transmitting heat in a refrigeration system. Typically, any fluid can be used as a refrigerant. It is just the how you manage the pressure of that fluid. Okay. For example, water can also be used as refrigerant. And as in latest news, there is a company in Germany which is trying to use water as a refrigerant. But the only problem with that systems is, that water boils at 100 degrees centigrade at atmospheric pressure. Now, if you want to use water as a refrigerant, you have to decrease the pressure. You have to come in vacuums to operate water as a refrigerant in the vapor compression system. And that makes the system bulky because you have very low densities, vapor densities, and so on and so forth. So there are a lot of things I will cover in these slides, but that's a simple example. Like any fluid can be used as refrigerant. It is just that how you manage the pressure. Broadly, the refrigerant can be categorized into two main blocks. First is primary refrigerants and the other is secondary refrigerants. So the basic difference is the primary refrigerants goes under phase transformation, and that is where the advantage lies. There is a phase transformation if from the liquid to vapor, as in evaporation, and vapor to liquid as in condensation. And the main advantage of two-phase heat transfer is higher heat transfer coefficients. That makes the heat exchanger designs and very interesting. And that is why these fluids are, typically clubbed into primary refrigerants. I will come into details about today. The topic discussion is actually focused on primary refrigerants. Will not touch base secondary refrigerants, but I will go into details how we deal with the primary refrigerants and what are the know-how about the primary refrigerants. Now I come to secondary refrigerants. These are the liquids which are used for transporting thermal energy from one location to another. They do not go under phase transformation. They are just cooled and they are used to deliver the energy. For an example, when you are in your college or when you are in your office or in a shopping mall, supermarket, let us say, you have water chillers. Like there is a chiller which sits on the top of the building. There is a refrigerant in the chiller. So the refrigerant cools the water, and the water which is cooled is used in the AHUs, air handling units, to cool the air, and which is used for our space conditioning. That is a classical example how we use water as secondary refrigerant. Even in the commercial refrigeration or in the supermarkets, you can use glycol loop, you can use water loop, and there are so many other options where you can use secondary refrigerants. Now, it is very important to note that secondary refrigerants have advantages as well as disadvantages. First, I will talk about the advantage. The advantage is that you can actually limit the exposure of refrigerants. For example, when you are using chillers, so the refrigerant is not necessarily to go and to get exposed to the human. They can be put upside on the roof, and the water is circulated in the AHUs, and the air is going to the exposure to the humans. Also, the charge of the refrigerant reduces, and which is very favorable for the flammables and the other toxic refrigerants. Will come in detail in the following slides. But the major disadvantage is that you are imposing an additional delta T, which is an negative point from the heat transfer analysis. Now you have an additional heat transfer interface, but there will be an additional resistance to the overall system, and that leads to inefficiency. But normally in the chillers, where we use heavy refrigerants, that inefficiency is negligible, and we have a dominancy of the advantages what I discussed. So we typically use water to cool the AHUs. So so this is the simple just the categories of the refrigerants in a very simple sense. Now, why we are actually studying the refrigerants and what needs to be understand is there are two typical major points. First is selection and the other is replacement, and I will discuss these two parts separately. So first is selection. You have so many refrigerants available in the market, in the literature. Now, which refrigerant to use in what application or for what system size? What are the initial cost? What are the operating cost? What is the safety of the system? What is the reliability? What is the serviceability? Are there any environmental issues associated with those refrigerants? So all these factors plays a vital role when you are selecting a particular refrigerant for a specific application. For example, I've taken very classic example. Let us take all of you know about one refrigerant. I'm just assuming, and I think my assumption would be pretty much correct. All of you know about R134A. I repeat, R134A. This is a medium pressure refrigerant, and this is suited only for the medium pressure applications. Why? Because when this refrigerant is used in low temperature, let us say -30 or -20, so it typically will require vacuum. Because its boiling point is nearly -26, -28. So anything below that, you have to go in the vacuum, and then your system charges and your cost and your other things, serviceability, everything goes costly or difficult to manage. So this is just an example, like how you decide an application of the refrigerant. Another example, if I take from the environmental, which is very pertaining at the moment and which is very a hot topic in the research at the moment, that is the ozone layer depletion and the global warming. So from the ozone layer depletion, you have an parameter which is known as ODP, ozone depletion potential. Okay, and from the global warming, you have GWP, global warming potential. So these two, ODP and GWP, these are the deciding factors nowadays for any refrigerant if it talk in terms of environment. So as of you all are aware, R22, R12, these were CFCs and so on and so forth refrigerant. These were having ODPs, and these refrigerants are phased out. Now we are having R134A and other which are HCFCs or HFCs. They don't have ODP, but they have GWP issues. So they are also again going into the phase out transition. So environmental strict rules and protocols also plays a very significant role in the selection of the refrigerant. So we will take this detail in the coming slide. This is just an overview, like how we can actually go around to have a selection of the refrigerant. Now there is a separate issue. Nowadays we have the replacement. Because of the environmental strict rules, we have to replace the high GWP or ODP possessed refrigerants with the environmental or low GWP refrigerants. So there are two possibilities. Either you retrofit or you have a new design. So what do you mean by retrofit? So by retrofit, you mean that a technician or a service engineer goes to a refrigeration plant, just take out the previous refrigerant and put a new refrigerant into system, and you are all set with only minor modifications. That is known as retrofit. And that is very difficult to find a retrofit solution for an existing high GWP refrigerant. Many companies and research institutes and universities work day and night to find out proper retrofit solutions. And you can find it anywhere in the literature. So you happen You have so many of examples quoted. Then you have new designs. Sometimes retrofits are not possible, and in seek to have good energy efficiency, environmental protection, we often go for new designs. And then that's a separate ball game where you have new system design, new architectures, advanced architectures. For an example, the latest advanced architecture might be, you would also be knowing that in a supermarket, we are now integrating the AC and the heating loads. That means you have a single unit which will satisfy your refrigeration, your AC loads, as well as your heating loads. And that is known as a fully integrated system. So that's a new design altogether, and which is very effective, easy to maintain, and very energy efficient, because you are utilizing the energy at each and every corner possible. Okay, so we can go in much details in the coming slides. Anybody please confirm that is my voice and connection, everything okay or fine? Like, are you able to hear me properly? Anybody can confirm? Hello? Anybody can confirm is my voice? Everything fine?
Yes, sir, fine, fine.
Fine. Okay. Perfect. Perfect. So coming back to the points, let us study about the group of refrigerant. I know that some of you know this pretty much more than me, or you are reading about this, but just an overview, just to have the flavor of the different groups of the refrigerants. So initially there were only natural refrigerants. The oldest refrigerant is ammonia, water, CO2, and then the synthetic refrigerants came up, and the first man-made refrigerant was CFC, chlorofluorocarbon, and the example is R11, R12, and so on and so forth. And they were produced in mass, and they were actually marketed well, and they captured the market due to easy operation, higher energy efficiency, safe operations, and that actually lead to the globalization of in the terms of refrigeration systems. And you had some issues with this refrigerants. That is, it had ODP values as well as the GWP. So then the environmentalists and the researchers looked into this matter. They come up with HFCs. So they had the less ODP, but still they had the higher GWP. Some of the example is R22, R142B, which is used widely in the foam blowing agent, but nowadays it is banned. And then going forward, you had HFCs, hydrofluorocarbons. So you eliminated the ODP issues, but still you had the GWP values. But these refrigerants are still widely used in the developing countries. Some of the examples is R134A, R404A, R410A, and so on and so forth. So these were typically the biggest inventions, you can say, in the refrigeration industry: CFCs, HCFCs, and HFCs. So now only HFCs are allowed in some of the developing countries, also in some part of the developed countries, following the strict guidelines of the environmental policies. There is another group of refrigerants, which is HFOs. They have no ODP and they have very, very low GWP. However, they have some issues with the flammability, but typically that can be addressed. I will come in the coming slides. And HFOs are majorly used to blend the other refrigerant. So these find their application in most of the blendings. I will come into that point later. And the last group is the natural ones, and which is also gaining very, very significant importance in most of the European and the developed countries, also in the Asia nowadays. So, and typically there are 3 natural refrigerants, or you can say 4. That is propane and isobutane, so, and CO2 and ammonia. So you would be very much knowing that R600A isobutane is widely or universally accepted in the domestic refrigerators. That is you can go into any shop, or after this meeting you can go and check at your domestic refrigerator if it is new buy, like maybe 2 or 3 years earlier, or maybe 5 years earlier. You can see the refrigerant used in that refrigerator. That would be R600A. If not, then it would be R134A. Okay, so these are some of the examples where the naturals are also fitting. For example, CO2 is going in commercial refrigeration, ammonia is going in industrial refrigeration, and propane is also going in commercial, but with some charge limitations because it is highly flammable, and you have to be very specific about how much charge you can use of the flammables. I will come to that, in the coming slides. On the right to your screen is just a table which shows all the refrigerants in that order what we have read: CFCs, HCFCs, HFC, HFO, and the naturals. And you can see what is the ODP and what are the atmospheric life and GW values. So you can see that the ODP for R11 is 1. That is the reference for measuring the ODP. And on the bottom, you can see R744 CO2 that has a GWP of 1, which is the reference for measuring the GWP. So these are the groups of refrigerant. Going forward, now you have so many refrigerant available in the market, and different chemical structures, compositions, properties, and everything, molecule structures, and so on and so forth. How anybody can know from just name what kind of molecule you are talking about? So ASHRAE came up with a designation rule so that anybody or the general public can understand which type of fluid we are talking about. So ASHRAE, just like ISHRAE, you have ASHRAE, American Society of Heat and Refrigeration Air Conditioning Engineers. They come up with the generalized rule where you can actually give a name or a designation to the group or a refrigerant. So what is the advantage of common designation? That is, from that single number you can get very useful information like the type of refrigerant you're talking about, its chemical composition, its molecular weight, and not what there are so many things that you can extract from just from the name of the refrigerant. They give the unique way that you have to give R at the starting, and then followed by a unique number, which we will be studying, and we'll be learning together how we can name a refrigerant. You can, after this class or after this session, you can go and you can Google and you can find ASHRAE standard 34, which broadly has this designation, and you can go and deepen your knowledge. So in the left bottom, you have a table where you have series of the refrigerants and the corresponding chemical group's name. So the 00 series, 000 series is methane based. The 100 series is ethane based. The 200 series is propane based. The 300 series is cyclic organic compounds, and so on and so forth. You can see on the screen how we are giving the chemical compositions series names according to the ASHRAE designation. So let's do a simple example how we can designate the refrigerant. I'm sorry, this is a very busy slide, but I will try to make it simple. Okay, so first you look at the left uppermost corner. So you have number 1, which is fully saturated halogenated compounds. So these compounds or these refrigerants are typically the derivatives of alkanes, and the alkanes have a formula CnH2n+1, where C is carbon, H is hydrogen, and the N is the number of the carbon atoms. So if N is 1, then you have CH4, that is methane series. If you have NS2, you have C2H6, that is ethane series, and so on and so forth. You can make the alkanes from varying the N, which is the number of carbon atoms. Now, how we can name this type of refrigerant? What is the rule for naming this type of refrigerant? So the general rule is R followed by X, Y, and Z, where X plus 1 indicates the number of carbon atoms. Y minus 1 indicates the number of hydrogen atoms. And the Z indicates the number of fluorine atoms. Now, if there is some balance out of these, then that will represent the chlorine atoms. Okay. So just look at the right side now, right side upper corner. We can do an example of what we have read like this. So example is R22. In this, the X is 0. It means the number of carbon atoms is 0 plus 1, which is 1. So we can say that it is a derivative of methane, because your N is 1. So you have CH4. That is a derivative of methane. Then the Y is 2. So how will you find out the hydrogen atom? That is Y minus 1. So you have 2 minus 1, 1. 1 is your hydrogen atom. Then the Z is 2. That is the number of fluorine atoms. Now what is the valency of carbon? It is 4. So the balance is 4 minus the number of hydrogen plus your the fluorine atoms. So that is 4 minus 1 minus 2, and that is 1. That's why you get how many chlorine atoms? 1 chlorine atom. Then your last chemical formula of R22 becomes CHClF2, because you have 1 hydrogen atom, 1 chlorine atom, and 2 fluorine atoms. And this is CHClF2. Similarly, you can do a small practice of R12, R134A, R410A, and so on and so forth. So this is a very simple, example how you can, designate the refrigerant. Now, just focus on R134A. If you can see on the right side bottom, I've shown 2 figures. R134A on the left figure and R134 only, not with A, on the right figure. So the letter A at the end of refrigerant, small a, that denotes an isomer. That is an isomer. What is an isomer? Isomer is having same chemical composition but different atomic arrangement. Just focus on the bottom figures. If you see R134A, you can see that its chemical formula is C2, H2, and F4. 2 carbon atoms, 2 hydrogen atoms, and 4 fluorine atoms. So you have 2 carbon atoms and 4 fluorine atoms and 2 hydrogen atoms arranged in a typical, structure. The same you see on the right side, only the positioning of the fluorine and the hydrogen atoms is changed, and that is the isomer. But the chemical composition is same. And please note that the arrangement of the molecule is very important in deciding the resultant properties. Hence, what I want to say that R134A is a good refrigerant as compared to R134, and only because they both have same composition, but the atomic structure is different, and which gives R134A as a lead in the thermodynamic and heat transfer properties, which is very important in refrigeration. Okay, so there are other examples where you can consult some book, literature, or even the HVAC 34 standard. So this was the designation rule for fully saturated halogenated compounds. Just an example what I've given you. Now there is another other kind of compounds like inorganic refrigerants. So mostly, natural refrigerants such as ammonia, carbon dioxide, nitrogen oxide, and even water, they are inorganic refrigerants. And for them, the rule to designate is very simple. You just have to start with number 7, and then you have to follow by its molecular weight, rounded off. So let us quickly understand by an example how we can name any inorganic refrigerant in a scientific manner. For example, ammonia. So ammonia is NH3. So the molecular weight is N is 14, H is 1, 3. So 14 plus 3, 17 is the molecule weight. So the designation would be R and 7. So that is fixed, and followed by its molecular weight. That is 17. So R717 is your ammonia. Similarly, carbon dioxide has a molecular weight of 44. So its name is R744. Water has molecular weight of 18. So your designation becomes R718, and so on and so forth. You can give the other designation. So I have taken only 2 examples. There are other ways of also naming the designation, but due to the time limitation, I cannot go into much details. But I strongly recommend to to study the literature and get acquainted with this naming, because it gives you very useful information about its chemical compositions and the structure. Now, we now know that the refrigerants are of 2 types, primary, secondary. We know that how we can designate it. Now, how we can classify them, that is also very important, because this classification will actually decides its application limitations. So on the right side, you have a small table. So we will come to this later. First, focus on the left side, text. So we have 2 types of classification. Just try to concentrate. First is toxicity, based on the toxicity, and the other is on the flammability. Now, what is toxic and what is flammable? I think that all of you know. So based on the toxic, we can divide the refrigerant on the category of A and B. A is low toxic, B is high toxic. It's very straightforward. Secondly, based on flammability, you can divide the refrigerant into 3 classes, or eventually 4 classes. First is 1, second is 2, third is 2L, and fourth is 3. And 1 to 3 is in the increasing flammability order. Means the class 1 is non-flammable, and the class 3 is highly flammable. And the 2 and 2L, there is a very slight difference between 2 and 2L. So the 2 is mildly flammable, and your 2L are the lower flammability refrigerant, which has a burning velocity of less than 10 centimeter per second. Now, what is a burning velocity? If you burn refrigerant, from which how much the velocity of that flame is, if you measure that, and if that velocity is less than 10 centimeter per second, your refrigerant will be 2L. If it is more than 10 centimeter per second and less than 40 centimeter per second, it is 2. And if it is more than 40 centimeter per second, it is 3. Now let us try to give an examples of all these classes. First, before giving the example, what is our desire to have? We should have the lowest toxicity, which is A, and we should have the lowest flammability, which is non-flammable, that is 1. So my desire for every application should be A1, which is low toxic, non-flammable. And my worst choice is B3, that is toxic and highly flammable. So A1 to B3. Now you please see on the right table and you will understand what we have like we have just now read. So if you see on the decreasing order, you have the higher flammability, lower flammability, and no flame propagation. And from left to right, you have toxicity, lower and high. So A3, A2, A2L, A1, these are in the decreasing order of flammability, lower toxicity. B2, B3, B2, B2L, and B1, these in the lower, decreasing order of flammability and higher toxicity. So what we require is A1, that is our best choice, and the worst choice is B3. So now quickly we will give the examples. So you can see that on the left side bottom you have examples. So the A1, which is our best choice, is eventually R22, and you know that this is widely used in the room air conditioners in supermarkets, and now you understand why this refrigerant is widely used, was widely used, or is also used nowadays also in some other part of the world, not everywhere. R404A, this refrigerant goes in commercial refrigeration worldwide. R407 series, all series A, B, C, D, and there are till H, all are used in commercial refrigeration. R410A, this is used in air conditioners or chillers, okay, and so on and so forth. Then you have A2Ls. A is low toxic, 2L is lower flammability, and these are the HFOs. A2Ls are the typical HFOs. What we have learned in the groups of refrigerant, hydrofluoroolefins, and these are the two classic examples are R134YF and R134ZE. Now we come to A2. You have A2 means lower toxic and mildly flammable. These are R142B, R143A, R152A. Okay, and then there is A3, that is lower toxic but highly flammable. And both the hydrocarbons, propane and isobutane, these are A3. But however, they are used with the typical risk analysis. And then the ammonia, which happens to be the best refrigerant in this world, thermodynamically or by performance, is B2, and which we don't want, because 2 is lower flammability, that is it is flammable, and B means toxic. So hence dealing with ammonia is really typical, and hence it is only used in industrial refrigeration, where we have typical mitigation strategies, how to handle with refrigerant, how to dispose the ammonia properly, and how to deal with the leakages and the handling of the refrigerant. Okay, so we can take questions on this later. Okay, now going forward, we have so many refrigerants, like other different types of refrigerants. Then why we do need to blend a refrigerant? Blending of any refrigerant is important because we need to extract certain properties or certain benefits out of each of those refrigerant put together. For example, you have two refrigerants, let us say A and B. The A refrigerant is flammable, but it is highly, it is very good in thermodynamic properties. And the B is not good, but it is flame suppressant. So what I can do, I can mix A and B in some of the ratio so that my A, which is flammable, becomes non-flammable, and the resulting refrigerant is non-flammable plus having good thermodynamic properties. And that is what the advantages we get from the blending of the refrigerant. But having said that, it is not a straightforward approach. It is very deep chemistry understanding goes into it, and there are other consequences while blending the refrigerant. You may end up having a very large glide, and which we can, we will learn the glide right now. And you can also have the, you can, your properties may shift to other dilemma which we do not require. So there is a lot of things goes around the blending of refrigerant. Typically, why we do the blending? That is to reduce the flammability, to increase the volumetric capacity, which is kilojoule per meter cube, and also to limit the discharge temperatures for any refrigerant. There can be more objectives. I have only put 3 objectives which are very particular for the today's presentation. Okay. Now, what are the types of blend? There are 2 types of blend. Whenever you mix any refrigerant, you will end up in either of the 2 blends. First is zeotrope, another is azeotrope. Now, what is an azeotrope and what is an zeotrope? I will come this point later. But let us understand what happens when you blend. So I need your attention at this point. Please try to understand the things. I will repeat it, very slowly, that what are the bubble point, what are the dew point and zeotrope, azeotrope, what is glide and everything. Okay. Now, just imagine you have a container, you have a vessel or a container. You have 2 refrigerants, A and B. The vapor pressure of A is higher than vapor pressure of B. Okay, or let us say boiling point. The boiling point of the pressure of the refrigerant A is higher than refrigerant B. Now you mix A and B in a vessel. Okay, so you mix A and B in a vessel. What will happen? At equilibrium, the higher pressure molecules will try to go in the vapor space because of their higher pressure, and which is the refrigerant A, and your lower pressure molecules, which are the refrigerant B, they will stay in the liquid. Okay, so this phenomena of separation of liquid and vapor phases in a vessel is known as fractionation. So your mixture or a blend A plus B is now fractionated. It is fractionated into 2 different composition. First is vapor composition, which is rich in refrigerant A, and the liquid composition, which is rich in refrigerant B. Okay, so till this we have a vessel. I will again repeat. You have a vessel, refrigerant A and B. You mix them. Refrigerant A has higher pressure. Refrigerant B has lower pressure. When you mix this both of the refrigerant in the vessel, they both will fractionate into 2 composition. The vapor composition will be rich in refrigerant A, which is having higher pressure, and the liquid will be rich in refrigerant B, which has lower pressure. Okay. Now, this is a scenario that you have a fractionated vessel, refrigerant vessel. You have refrigerant A on the top, B on the bottom. Okay. Now you heat it. You are trying to heat it. You are trying to boil it. So what I supposed to have, like, the higher pressure molecule will boil off at first, and then the lower pressure molecule will boil. That is the physics. Okay, and that is the only the definition of glide. That is the difference between the boiling points of vapor pressure, higher vapor pressure fluid and lower pressure fluid. At 2 different temperatures they will boil, and the difference between that 2 temperatures is known as the glide of that refrigerant. Okay, now you just see on the left side bottom figure, and from here you will get a good understanding of the glide. Okay, so if I go on the x-axis, X-axis is the mole fraction of more volatile component, means more pressure component. And the y-axis is the temperature. If I start from the zero on the leftmost side, you have, one temperature only, and which is of the, let us say of the A composition. Okay. As soon as you go on the right and you start adding B composition into it, you are putting fractionation into it. Then you have two types of compositions, vapor and liquid, and they both start to boil at different temperatures, or they both will have their different vapor temperatures. And that is the dew point line and the bubble point line. Dew point means vapor and the bubble means liquid. And the difference between these two is known as the glide. Okay. Now you see on the right, okay. In case, now we can define the definition of, zeotropes and azeotropes. Now, when you blend any refrigerant and your glide is negligible, or if A and B pressure are B fluid are very close in their boiling points, they will try to form azeotropes, means A and B like each other, and there will be no significant difference between their bubble and dew point, liquid and vapor point, and you will have almost negligible glide, zero glide. Okay, and that is the rightmost upper figure. If you see pure fluids or azeotropes, you have a single straight line under the vapor dome. That denotes that at each and every point under the vapor dome, you have similar temperatures of liquid and vapor, and that says that is azeotropes. And ASHRAE designates azeotropes starting from 5, like what we learned in the previous slide. Inorganic refrigerants start from 7, like R717 ammonia. So the azeotropes, the blends, will start from either 4 or either 5. 4 is for zeotropes, which has glides, and 5 is for azeotrope, which don't have glide or insignificant glide. Okay. So now if I go back, I go back and goes to see the examples. If you see the example in A1, 404A, so it is starting from 4, means it's a zeotrope, it has a glide. And if you see a refrigerant R507, which is, azeotrope, because it is starting from 5. 5 is the series for azeotrope, and the 4 is series for zeotropes, which has glides. Okay. Now let us try to understand in detail about the azeotrope blends. Okay, I've taken some example, very simple examples, and which are typically known in the industry. Okay, what is the azeotrope blend? It is a stable mixture of 2 or more several refrigerants whose vapor and liquid phases retain their identical composition over a wide range of temperature. Okay, so there are typically the azeotrope pairs which are widely used in industry. For example, R32 and R125, R134A and R125, and so on and so forth. Please concentrate on this slide. I will give a very classic example of the most widely used refrigerant in today's industry, and what was the intent to blend it, how the physics was behind it, and how interesting the things was to make this blend. Okay, so my example is R32 and R125. Okay, which is on the left side of the figure in the bottom. Okay, so R32 is a HFC and R125 is also HFC, which means both have high GWP, but they both don't have any ODP. Okay, so that's why they are still used in some part of the country. Okay, R32 is flammable. It is A2L. R32 is A2L. It is flammable. And R125 is A1, which is low toxic and non-flammable, and also very, very strong flame suppressant. It is widely used in many industries as a flame suppressant. Please note R125. It is used as flame suppressant in many industries. It has typical orange flavor, orange smell, R125. Okay. So if you mix R32 and R125 in the ratio of 50-50% by mass, you typically, depresses the flame of R32. Means your R32 will be non-flammable now, or the blend of R32 and R125 is non-flammable, and that can be treated as A1 and can be used in many applications then. And that is the blend known as R410A. R410A, which is widely used in your home ACs as well as in chillers. It's a very high pressure refrigerant, widely used in home ACs and domestic air conditioners and chillers. Okay, and if you can see in the figure down, you have the graphs. These graphs are drawn by me. You can see the T liquid and T vapor. Means after fractionation, if you put R32 and R125 in a vessel, they will fractionate in vapor and liquid phases, and the individual temperatures of the phases, these are very close, if you can see. Okay, and which says that these are typically having zero glide or negligible glide, and that's why they can be treated as neo-azeotropes or azeotropes. But for this example, R410A, they have some glide at higher percentage of 125A, and hence this is termed in 4, not in 5. Okay, so you can see from figure below 40% of 125A, you have all azeotrope, the line coincidence. But after 40%, there is a slight difference between the both temperatures, and which is a classical example that why we are not giving R410A, which is a blend of R32 and R125 by 50-50% mass composition as azeotrope. Okay, and on the right you have an example of R143A and R125A. This is a typical example of R404A, which is used in commercial refrigeration. So this is just a general idea what is azeotrope and what is the so now you know that why we blend and what is the need of blending. So this is an example of zeotropes. What are the zeotrope blends? So the zeotropic mixture is one whose composition in liquid phase differs to that in vapor phase. Yeah, that is what I'm saying from the previous two slides. When you mix any two refrigerants in a vessel, there will be fractionation, and if the composition of liquid phase is not same as vapor phase, that means it is a zeotrope blend. In other words, in the vapor phase, the higher pressure molecule will be more, and in the liquid, the lower pressure molecule will be more, and that is the imbalance which leads to its zeotropic behavior, and you will have a significant glide. As you can see, typical examples given in down figures, you have a significant difference in the liquid and the vapor temperature under certain pressure condition. Okay, so these are the zeotrope blends. Okay, I know that this thing, seeing maybe some of the students may be seeing this at first and it will be a bit difficult to understand, but I also have a time limitation, but I'm sure that with this general idea, now if you go back to your literature or books, you can understand it pretty much easily. And I will recommend to do some practice. Okay, like if you have Excel or if you have some kind of computational platform, you can try to extract the properties which are available either in the commercial packages or freely available in the literature, and you can try to play around with the blends, and you can see how this blending is very interesting. So you can see at your academic level or at your professional level. Now this was about the blends. Now in an industry, refrigerant is very costly parameter, We don't want the refrigerant to get leak. And these are the two reasons why we don't want. First is the cost. Second is the environmental issue. And the third is the safety issue. If your refrigerant is leaked in the environment, it has significant environmental as well as safety consequences, as well as the economic consequences. So there are the devices where you can typically, you can, detect the leak at the initial stage, and you can repair them so that your bulk refrigerant is not leaking from any site. And that is very important from practical perspective, to know the devices used in the leak detection. Okay, because why I'm taking this topic, because some of the students which are in final year, or maybe will be go to work in the industries, and you would see this kind of equipments. If you'll end up in an air conditioning company, or wherever possible, there would be another process industries where you will be using different kind of leak detectors. But you should know, you should have an idea about the different type of mechanisms which can be used in the leak detection. This is only two examples I'm shown. I'm pretty sure there are various other ways to measure the leak. Okay, so this is just a motivation. So for that you can see the other ways of leak detection. So the first and the most simplest leak detection, which I have not shown in the slide, is soap bubble method. That is simplest leak detection method. Soap bubble method means you just put the soap on the leakage site, and you see the bubble out of it. All of you have seen on the shop of a puncture, okay, of your vehicle tire puncture, how you see the leak. You apply soap and you see in the water, you see the leak coming out from there. Okay, so that is the simplest way to have the leak detection. But why that is not possible at every site? Because some sites are very internal in the system, or are very, very small, which are not easily detectable by soap. And also the soap with water can ruin your electrical components in the system. So it is not highly recommended always to use soap bubble method. But wherever it is possible to use soap bubble method, people use it. Okay. Then the other method is halide leak detector method. Here you use the chemical reaction which takes from by the refrigerant molecules with the acetylene gas, and the color of the gas changes, and which gives you the indication that there is a leakage from this site. But this method is not recommended to use with flammable refrigerant, because you will end up in the fire. So that's the limitation for this kind of leak detectors. Then you have the modern type of detectors, electronic leak detectors. Here you see that you have a tube where the refrigerant goes into it. Okay, and there you have electrical circuit. Okay, where the ions are separated, and based on the ions amplitude, there you have a sound from this equipment. For example, if the air goes, only air goes into the tube, the ionic separation is less. You have less sound, or maybe no sound, based on the typical setting. But if there is any refrigerant mixed with the air, in the event of leakage, the ionic separation would be more, and that would be amplified in the sound way to let you know that there is some leakage. And there is a very typical advantage of this system. If you go near to the leakage, the sound will go up. And if you go away from the leakage, the sound will go low, due to the typical amplification of the ionic separation. And that is why it is very, very accurate in actually finding the exact location of the leakage. Very close location you can find from the electronic leak detectors. There are various other methods where the industry follows for the leak detection. I recommend to see from your literature or from any reliable source. Okay, so seeing the time, like we are getting short, let us quickly come to this is the most important part of the of this session. What are the desirable properties of the refrigerant? Okay, please don't go to this slide. This is very busy. I'm so sorry. This is a lot of information on this slide, but I will try to put the information in very simple ways so that you can understand. So typically, if you see on the right side upper corner, there are only two types of properties which we look into for any refrigerant. First is thermodynamic and thermophysical. That is the foremost important property selection criteria. What are its thermodynamic and thermophysical properties? And the second is, which is also very, very equally important, that is environmental and safety properties. From environmental, I will say ozone depletion potential and global warming potential. And from safety, the combustibility, how flammable it is. And at the last, we can say the economics of that refrigerant. So when you are in professional, industry or somewhere, the economics also plays a very, very significant role. So these three parameters are the three different properties desirable where you will find interest. And I will try to put them, in the pieces. I have talked about the environmental properties. Okay. I have talked a bit of economics. And now it is time to talk about the thermodynamics and the thermophysical properties at a large. Okay. So the first important property is, now you see on the left, that is the first property, that is the latent heat of vaporization. This is the most important property. Okay, because that is the heart of the process, the evaporation process or the condensation process, where you extract the heat from the source or the sink, wherever you want to extract the heat, and you reject the heat correspondingly in the other process. So the latent heat of vaporization, typically we say HFG. This is the very important property of the refrigerant. And this also, along with the density of the refrigerant, defines the capacity of any refrigerant. Okay, so this is the most critical property of any refrigerant. So what we desire, we desire higher heat of vaporization always. That is our first point to note, that we want always high latent heat of vaporization. Okay, coming to second point, that is chemical stability, or this should be chemically stable, very straightforward. Then we take the cost and safety, all that. We need a non-flammable, we need a cost-effective solution, we need the compatibility with compressor lubricants and materials and so on and so forth. Okay, then come to the fifth point, that is the pressures, suction pressure and discharge pressures. These two thermodynamic properties are very important. You need a suction pressure which is higher than atmosphere. Why? If you work in vacuum, there are two typical problems. First is the outside air or outside non-condensable goes into your system. Second, at lower pressures or at vacuum pressures, your density is very low. That makes your system bulky. Okay, that's why you need high suction pressure. But there is a limit in how much high you need. Okay, because if it is very high, then your cost of protecting that system becomes high. For example, in CO2 has a very high suction pressure. So your tubing cost is high because you have to save the refrigerant from coming out of the system. So your tubing cost becomes high. So typically we require suction pressure that is 2 or 3 times, 4 times higher than the atmosphere, and that is always desirable. Okay, higher suction pressure also leads to smaller displacement, compressor displacement, because of the high vapor density. Okay, so it can suck more refrigerant at a go, and that will require higher compressor displacement, smaller displacement. I'm sorry. Now I come to the discharge pressure. So at a given condensing temperature, it is always recommended to have lower discharge pressure so that your compressor power is low. Okay, and it is easily manageable in the given constraints. Lower discharge pressure reduces your construction of compressor, your condenser, your piping, and so on and so forth. It is very advantageous to have lower discharge pressures. Higher suction, lower discharge, which means lower pressure ratio, and which means higher compressor efficiencies. So all going in the favorable directions to have a good refrigeration system. Okay. So just come to the left side of the slide. Again, this slide is busy. Just come to the left side of the slide where you see the latent heat of vaporization, what we have studied. Okay. And you see pressure ratio. Okay. Now there is a typical, thermodynamic equation by Klaproth and Claren, which relates the latent heat of vaporization with the pressure ratio. Okay, so please pay attention here. This is very important, and see how typically the nature gives you the trade-off. You always cannot get everything from the refrigerant. Okay, that is very important to understand. So I'm talking about two properties. First is pressure ratio or the compression ratio. Okay, so this means that pressure ratio should be small as possible for our high volumetric efficiency and low power consumption. For a good compressor, the lower pressure ratio is favorable. Okay, but if you see the equation just below it, it says that those fluids which have a low pressure ratio, they have low HFG or low latent heat of vaporization, and which is not required. We need higher heat of vaporization, which means if you need higher heat of vaporization, your pressure ratio automatically increases. And if you decrease the heat of vaporization, your pressure ratio decreases. So these two contradictory things requires a trade-off. And the classic example of this, of this theory is the refrigerant R32. R32 has a very high heat of vaporization. Hence, its pressure ratio is high. And that's why we have a significant problem with the discharge temperatures. Okay, I'm not going into much details into that, but that's just an example just to let you know that everything is not possible from the refrigerant thermodynamically. So the molecules with higher heat of vaporization, such as R32, will have higher pressure ratios. Okay, and the lower heat of vaporization molecules, such as R22 or maybe other in respect to R32, have a lower heat of vaporization and lower pressure ratios. Okay, I know that there would be some doubt on this, and I will be happy to solve at the end of the presentation. Okay, so please wait till the end of the presentation. I'm talking a lot, but let us see the doubts at the end of the presentation. On the right, you have some other properties, and which are typically known as thermophysical properties. What are thermophysical? So thermo is specific heat and thermal conductivity, and physical is density and viscosity. So it's very straightforward. You need lower specific heat of liquid so that you have good amount of subcooling. You need higher vapor specific heat so that your superheating is low. You need higher thermal conductivity, both of liquid and vapor, and you need lower viscosity of both liquid and vapor. This is very straightforward. Higher thermal conductivity will give you better heat transfer and equipment size, and lower viscosity will help you to reduce your pressure drops. Okay. Now, apart from this, there is a general theory that we need to understand, and that is very interesting philosophically, where we hit the limit of deciding or selecting a refrigerant, and what are the limits all around. Okay, that is shown in the bottom diagram or the bottom table. where you have hydrogen, chlorine, and fluorine triangle. Okay, there you have hydrogen, chlorine, and fluorine triangle. Please try to concentrate on this, and this will give you an entire philosophy of where the industry and research is going for selecting or searching a new refrigerant or existing refrigerant. Okay, so what are the limited combinations? So the first point is adding chlorine or bromine increases your ODP. If you add chlorine or bromine, you are adding ODP to it. I'm talking about a blend. Okay, so this all talk now. What I will say will be around how when we are making a blend. So if in a blend, if you are adding bromine or chlorine atom, you are increasing the ODP. Okay, if you are adding fluorine, you are increasing GWP. And if you are adding hydrogen, you are increasing the flammability and lowering the atmospheric life. And believe, these are the three typical molecules, hydrogen, chlorine, and fluorine, where all refrigerants float around. Okay. So typically hydrogen is more dominantly in the HFOs, and that's why they are pretty much flammable. Okay. And the chlorine are in the HFCs, CFCs and HCFCs. That's why they have ODP. And there is more fluorine component in the HFCs. That's why they have high GWP. So that's why everything is not possible. There is a limit where you can reduce, or where you can hit ODP, or where you can reduce GWP, or where you can reduce the the hydrogen or the flammability. Okay, so this thing you have to understand. So whenever you are blending a refrigerant, these three molecules will come. Okay, and the amount of these three molecules will decide the nature of the blend. Will it have a ODP? Will it have a high GWP? Will it have a lower or higher flammability? Okay, but I'm pretty sure that nobody now adds chlorine or bromine because it is strictly not allowed to have ODP. But the fluorine is still going into the blends, and which gives the GWP values. And of course, hydrogen gives you the flammability. There are other molecules also which comes into the picture, such as carbon, which is always there, and which gives you the other properties. But these are the three typical properties from environmental and flammability perspective. Okay, I can take the doubts at the end of the session. Okay. Now there is a simple, very short talk about the evaluation of the refrigerant. So I typically know that you are at the fifth day of the presentations, and you have seen different slides, and maybe many of have given you the talk about how the refrigerants are evolved. So I will not pitch more on this slide. Just to give an overview, we are actually on the circle now. We started with naturals, and now we are back on the naturals due to the different environmental and phase outs and different policies which are going worldwide to protect the environment. Okay, so going forward, only naturals and the refrigerants which have lower GWP and no ODP will exist in the world. Okay, all the refrigerant with ODP and high GWP, or even with high GWP and no ODP, will be banned or eventually phased out. Okay, so only the refrigerant with low GWP and no ODP, and of course naturals, which will be the future of the refrigeration and air conditioning industries. And in those, the HFOs will play a significant role because they have low GWP and no ODP. Key drivers, you have mostly European F-gas regulation, you have Montreal Protocol, you have SNAP in US, You have, legislation in Japan, so Asia, Europe, America, all worldwide, there are different types of, agendas which are typically driving the evolution of refrigerants. Okay, fine. So uh, by this, I will, simply take, some understanding of the supermarket refrigeration system, and just a brief overview, so that like what are the typical configurations which are used in commercial refrigeration. So for those folks who are listening this time, supermarket refrigeration for first time, or not much familiar to it. So we have typically, commercial systems installed in the malls or in the shopping malls, in the, your supermarkets, where you can buy the items. So we need to keep that stores in under, some required temperatures and some required conditions, and which are listed in the rightmost down, you can see. So there are typically 4 loads in supermarket. First is low temperature load, which is in the range of -35 to -20 degrees centigrade, where you store the frozen meat, let us say, okay, or maybe other things which are, you need to deep freeze. Then you have refrigeration medium temperature loads, which are -5 to +5. Your ice creams, your dairy, and other things, they come under MP levels. Then you have air conditioning load, because the people are coming into your supermarket. They would be staying there. They would be buying, paying, and then going. So you need to maintain that conditioning space, and which comes on the air conditioning load. And then the last is space heating and tap water heating. That is in the winter time. Again, the people will coming, they need the space heating. And also somewhere in the process part, you also need some tap water heating loads. So these are the typical loads in the supermarket. And just to, by the way, supermarket consumes 17% of the global electricity used. And this information is pretty much 3 to 4 years old, I can say. So maybe this would have gone 1 or 2% more now. So better to assume it 18 to 19% of the, approximate global electricity used is for supermarket refrigeration worldwide. That's why it is very important to know which refrigerant goes into the systems and what are the different configurations. Okay. So this is a typical supermarket profile. I have already, already covered this slide in my talk, but I need to just give you an overview. Like what are the typical components which you can find in a supermarket? If I talk in terms of refrigeration system, okay. So you will have certain square foot of space available. There would be some refrigeration racks. There would be some display racks where you can see the products and buy. There would be some walk-in evaporators, means you can walk in and you can choose the product and come out. Okay, and the typical refrigerant used is R4, not 4A worldwide. And this is worldwide used. And nowadays there is some refrigerant which is retrofit for this, but I will not go into the detail for that. Typically 3,500 pounds is the charge size which goes into these systems. And the annual electricity consumption is in 2.4 mega kilowatt hour, which is huge. And the annual leakage rate is 35% from these systems. Nowadays, this rate would be lower than 20% maybe, because this data is typically old. I've taken from 2005 data. Sorry for that. And so now you can imagine 3,500 pounds of your refrigerant, and annual leakage is around 35%. So see how much high GWP refrigerant is leaked into the environment. That's why it is very important to adopt the lower GWP refrigerants. Yeah. So this is the impact of leakage. Now, whenever you have a leakage from a system, there are 4 impacts. First is economic impact. Second is climate impact. third is energy impact, and fourth is equipment impact. Okay, and these four impact is directly linked with the leakage of refrigerant. So that's why it is very important to minimize the leakage of refrigerant, and which is also the hot topic in the research at the moment. So the folks who, so the guys or folks who are interested in, taking some research career or to study some more, so can also go into the direction where you can, have some kind of ways where we can, reduce the leakage. At the same time, we are adopting the low GWP refrigerant, but the way to reduce the leakage will be, we will also well appreciated worldwide in the research community. Okay, so the typical configuration is the, centralized DX system. Okay, so this is my last slide. So please, I'm sorry for this long presentation, but this is my last slide. Okay, this is a typical, supermarket configuration, refrigeration configuration. So you have three parts. Just focus on three parts. First you have the condenser part, which is typically placed on the rooftop. If you can see on the right side photo, on the right corner. So the condenser is put on the rooftop. Then you have compressors, which is the heart of the machine. That goes to the machine room, which is separate. This is not exposed to the people. Okay. So all the compressor in the racks, they are put in the machine room. And the lines goes through the condenser and the evaporator, which is placed in the exposure to the humans, where you have the display cases or the, the walk-in coolers, where you can select the product, milk or fruits or frozen things and so on and so forth. So what are the features like? What are the pros? It is very convenient. Every person in the refrigeration industry, from technician to the, to the each and management or any kind of people, is well equipped with this system. They know this, and this is a common practice. Okay, you have the available components, you have contractors in place, you have stakeholders in place, you have everything in place, and this can be, built and applied easily. But what are the cons? What are the disadvantages? You have very long lines, and typically they use high GWP refrigerant. Long lines, refrigerant lines, high refrigerant charge, and a high chance of refrigerant leakage and higher environmental impact. That's why people are looking for advanced configurations where we can reduce the line sizes, where we can improve the configuration to have lower GWP refrigerant going into the system in a typical way, and we can reduce the leak rates. We can overcome with the energy efficiency. Okay, and just ending with this presentation, I want to focus on the two main directions where these configurations are evolving. So now this configuration has a disadvantage that it requires non-flammable refrigerant only, because if you see here down here, the refrigerant goes to the evaporator and the human is exposed here. In case of event or fire, if you use flammables, it is highly risky. Hence the refrigerant has to be A1, and the A1 refrigerant tends to have higher GWP except CO2, which is 1 GWP. Other else, every refrigerant A1 at the moment is higher GWP. Only the refrigerant which are A2Ls or A2 have low GWP, maybe within 150 or 100 or whatever the regulation may be for the GWP. So we have to adopt some configurations which can handle A2Ls. So the classical example of the evolution of the supermarket refrigeration configuration is the distributed system. Like you have very, very small systems distributed in the supermarket system, and there you can use small charges of flammables. That is allowed from the standard. Okay. Interested folks can go and read about the distributed system more. And classical example is propane water system. You have CO2 cascade system. You have other in direct systems or the glycol based systems where you can have the, flexibility to use flammable refrigerant also in the supermarket configurations. Okay. So that is all from my side, because now it is 6:27 and I was supposed to end by 6:25. So I'm very sorry if I've taken a long time or I was very fast on some points, but this was from my side, and I welcome every doubt of the participants. Thanks a lot.
Thank you, sir.
Thank you.
Sir, now the question answers we take.
Yes, sir. So I have the questions.
So,
So Ashish Utage, how
yes.
to deal with the flammable refrigerants for domestic air conditioning applications? Very good question. So this is very simple. There are some standards where you are allowed to use some amount of charge of the flammables in the domestic air conditioners also. Okay, so you have to go to read the standard for the flammability charge size, what is allowed. Like for examples, you can use 1.2 kg of A2L in the system. Okay, so that's why the classical example nowadays, you have the domestic air conditioner using R32, which is A2L, which is not non-flammable. It is flammable. R32 refrigerant is flammable, but it is used in your domestic air conditioner because it is below the charge size allowed in the system, and that is fine. Okay, so that is how you deal with the flammable refrigerants for the application. Okay, there is no other way to deal with the flammable refrigerant. However, there are other risk mitigation parameters which are typically required in large systems where you have fire extinguishers and other things, but that is not typically for the domestic air conditioning application. Okay. Second question, sir.
Yes, thanks.
What is the atmospheric life of a refrigerant? Okay, so any refrigerant leak into the system, whenever it leaks, the molecule of that refrigerant, it actually disintegrates, and the time required to disintegrate totally is the atmospheric life. That is the life of a refrigerant which it will be staying in the atmosphere. That is the atmospheric life. Okay, and that is what we measure in terms of 100 years as an example for the CO2. Okay, that's why we have the GWP reference as 100 years atmospheric life equivalent to CO2. Okay, so the third question is Dilip Kumar. What is GWP? GWP is global warming potential, sir. Okay, this is a classical measure of the emission potential of any fluid escaping into the atmosphere. Okay, and it is measured in the terms of CO2 emissions with a reference of 1 for CO2, and yeah, that is GWP. Ashish Putake's another question. What are the different tests one should do for the commercialization of new refrigerants? Okay. What are your insights for research scholar working on developing new flammable refrigerant for energy efficient AC? Perfect. Okay. So, see, whenever you are developing a new refrigerant for commercialization, there are lot of other things which should go around it. First is your refrigerant should go under ASHRAE, ASHRAE nomenclature. You need to approve your refrigerant from the ASHRAE. Then you have to qualify the refrigerant for heat exchangers, for compressors, for its oil miscibility, for its elastomer miscibility, the sealings miscibility, and the environmental effect and the flammability. All the things goes into that. But my insight for the research scholars working on developing new flammable refrigerant would be like in the AC. Nowadays you have all options like A1 is R410A, A2L is your R32, A2L is your R452B, and A3 is your propane. I think Godrej company, I think in India is also using propane in your ACs. Okay. So developing new flammable refrigerants would be trying to to blend the individual molecules around this, working temperatures, and try to research that if you can come up with some good blend, and then you have to see its implications when you go into the commercialization part. But this is very, very, involved process, and requires a lot of, organized way to do it. Yeah. Then this is Ata Varis. Sir, from your point of view, considering present scenario of a country, which refrigerant you prefer in different regions of India? That is in Rajasthan, in Delhi, in South, in West Bengal, etc. Very good. So from my point of view, see, we have only two options. Okay, we have only two options in general. I will not say in particular. We have only two options in general. First is the natural refrigerants, which is of course very promising. CO2, propane, ammonia, all three are very promising. All are very promising. And the other option is the blends, which has HFOs and HFCs. That is also very promising. So these two categories would be, I see, would be coming in the coming years, which can be considering for the different applications. For example, CO2 refrigerant is a very good commercial refrigerant in the supermarket refrigeration if your climatic condition is low, because you will be in subcritical conditions and very excellent performance. So in India, let us say in Kashmir, or where you have very low ambient temperature, CO2 is a perfect choice. Okay, but in Rajasthan, where you have high ambient temperature, CO2 is not definitely a choice. Okay, where you have to think for other refrigerants, where they can, there is certain application range of refrigerant. Okay, you have refrigerant in your plate, CO2, the naturals, and the HFC and HFO blends. And now you have to choose in which direction or which application temperature range you want to apply, and what is the size of that equipment. That all things will come into mind. But from my point of view, yes, naturals, and the other is HFC plus HFOs blends. That would be the preferable refrigerants coming in different part of the country. Okay. A isomer, what is B? YF and ZE. Okay, I don't know what is B, but YF and ZE is the short form for R123 for YF and R123 for ZE. So, and these two fluids are the HFOs, hydrofluoroolefins. Okay, YF is R1234 YF and ZE is R1234 ZE. And let me also say you one thing more here, that YF and ZE both are in cis and trans form. Okay, so anybody from chemistry background can understand what is cis, CIS, and what is trans form. Okay, I left this open in the this discussion forum. Can go back and understand what is cis and trans. That it will give you a more deep understanding about YF and Z molecules. Okay. Avinash Soni, sir, what is the volumetric capacity of good refrigerant? It should be low or high. So volumetric capacity of refrigerant is kilojoule per meter cube, and it should always be high. That is our desire. Okay. So for example, R410A, it has a very good high volumetric capacity. R32 has a very high good volumetric capacity. But if you go for a refrigerant which is R1233ZD, it has a low volumetric capacity, but it has a very high energy efficiency. So there is a trade-off. You need to find an application where you require capacity or where you require efficiency. For example, you have a very, very large capacity chiller. Okay, let us say 2000 ton or more than that. There, equipment cost will be also important, and the operating cost will also be very important, because you will be spending a lot of money on the electricity. There you also need to have good efficient refrigerant, and that is why the trade-off between the volumetric capacity and the efficiency goes on. Okay, so generally it is very difficult to find the refrigerant which has both high capacity and COP. The only exception is R22. and which is unfortunately has ODP. So we have to phase out that refrigerant. Okay, it is very difficult to beat R22. Okay, in both in terms of capacity and COP. Okay, next question. What will happen if there is no blending of refrigerant? Okay, then you don't have any topic to research or to commercialize the blend, and there's no business and research. So let's go home and close this meeting. Just on a lighter note, I'm sorry. So the blending of refrigerant is important. That is the philosophically it is important, because this is the way how invention or the or the research or goes and develop and goes in a good manner. So the blending is very important, both in terms of research and also for the benefit of the humankind. Okay? Can carbon dioxide be used as refrigerant for all types of refrigerant needs, like residential, automobile, and commercial purpose? Quite a bit, yes. Carbon dioxide can be used in all types of refrigeration, like in residential, automobile, and commercial. Having said that, the atmospheric temperature prevailing that region is the deciding factor for carbon dioxide, because it has a very low critical temperature and high critical pressure. So the CO2 is good in the area where the annual ambient temperature is below 16 degree or below 17 degree. Okay, there it can be used in automobile, in residential, in commercial, anywhere. Okay, and people are doing good research. Eventually, my PhD thesis was on CO2 refrigerant only. Okay, so I did the thesis work on using CO2 in Indian climate conditions, and my results were not very promising and were very straightforward, because we have a very high ambient temperature. But there are very other ways where you can make CO2 to work in India, and like adoption of ejectors and subcoolers and two staging and so and so forth. But the economics of the bulking the system is also to be paid attention. Okay, while you are bulking the system. So my idea would be to have economics and energy at the same level to decide which refrigerant should go into the system. Okay. What is the significance of zeotropic blend? Yeah. So we have a glide. We have to deal with the glide, and glide is not always very bad. In glide actually helps in the evaporation, but it gives you determined performance on the opposite side when you're condensing it. So zeotropic blends, most of the blends are zeotropic, and you have to live with the glide. That is all. It is as simple as that. Okay. When you're mixing some compositions, you have to face the glide, and you have to deal with the consequence of the glide. But believe me, the industry has done it quite efficiently, and there is no such issue of using zeotropic blends. Okay. Which is the good software to see the behavior of the blends? Fine. I would recommend a combination of Excel and RefProf. Okay. And if you don't have RefProf, you can have CoolProf. Okay. That is freeware available, and so you can just combine Excel and the CoolProf and can see the behavior of the blends. But you have to be very cautious that for most of the mechanical students and the mechanical professionals, the blending looks very easy because we have the interaction coefficients. Okay, but I should remember, I should tell you one point, and you should make one point note that the interaction coefficient may take a lot of time to come out from experiments. I don't know the name of the refrigerant or the pair of refrigerant which took 10 years for them to come out with the generalized equation for the interaction coefficients. Okay, so RefProf or CoolProf can give you the equation for the interaction parameters, and then you can use the Excel with the CoolProf and can do it. MATLAB is also MATLAB and RefProf can be linked and can be do. There are lot of softwares nowadays available to do it. And if you use engineering equation solver, they have their inbuilt library for the refrigerants. Okay, So, and please mind it, I'm not doing any promotion of any kind of software. Okay, it is just in a letter note. Can you use thermal scanner? Next question. Can you use thermal scanner to detect leakage of refrigerant? Thermal scanner. I don't think so, because the refrigerant which is leaking in the atmosphere, if it is ignited, then only you can see the temperature change, or you can scan it by temperature wise. But as such, there is no reaction of refrigerant with the air, or there is no temperature change when refrigerant leaks from the system to the environment. So I don't know, but at the same time, I'm not sure. If you have a better answer, then please also update me if you can use the thermal scanner. But from my knowledge, I think no. How pragmatic is to have nano refrigerant in HVAC industry? Okay, fine. This is quite interesting, that you can add nanoparticles to the refrigerant to improve its thermophysical properties, but there are other consequences associated with that. That is the agglomeration of the particles from the base fluid. Then you have the interaction of the nanoparticles with the tubing, with the compressor, with the oil, with the elastomers, and there are a lot of things which goes into the HVAC industry. So see, you have to understand that any refrigerant to pass or to be adopted in HVAC industry has to go through a very long process of qualifying in each and every component. So now, if you want to use nanoparticle in the refrigerant, you have a new refrigerant altogether. And that new refrigerant has to pass from each test, from oils, from elastomers, from heat exchangers, from compressors, and from environmental agencies, from ASHRAE, and so on and so forth. So yes, it can be used, but I think that I don't see any commercial aspect at the moment. But yes, in the industry, in the research, it is gaining boom, and people can look into it. Yeah. What are the Indian standards for testing flammable refrigerant for AC? Typically, we follow HVAC standards for testing the flammable refrigerant, and that is standard number 14 that you can see for testing of flammable refrigerants. Okay, and also on this question, that's a good question actually. Starting with this, I should have given a slide on the standards. You should have we should also have all of us should have the standards with us, so that we can have the general idea how we can deal with the flammable refrigerants, and what are the performance standards and environmental standards going around the industry. Okay, what are the various methods used in decomposition of refrigerant? Various methods used in the, I don't think there are any method in decomposition of refrigerant. It automatically decomposes within its atmospheric life. And if there are any methods, then I'm unaware, and I'm sorry for that. You can ask to some other person, but I think that it automatically decomposes in the atmosphere when it is okay. There is one point in this question. So the refrigerant is always recycled. Okay, the refrigerant is recovered from the system, and it is used in the other systems if the system is stopped. Okay, so we typically never decomposes a refrigerant by our intention. If it is leak, then it will decompose it automatically. Okay, you can find more information if it is not satisfying you. Is there any blend in which no ODP and no GWP? No. Yeah. Any blend? No, there is no blend, but you have a refrigerant, that is water, which has no ODP, no GWP, and water can be used as refrigerant. And I will strongly recommend you to see, there is one German company which uses water as a refrigerant. Okay, you can Google it and you can see. This is the only refrigerant which has no ODP and which has no GWP issues. Okay. So liquid hydrogen is used in freezing and is abundant in nature as well. Then what is the possibility of using it as refrigerant? my knowledge is not limited to nitrogen. So I think that nitrogen will be flammable issue. That would be the first point. And there is other flashing issue of the nitrogen, which typically I don't remember the temperature where below that we have to use nitrogen. There is no other option. But above that, we have a good system VCR, and we are happy with that. Industry is happy with that. Okay.
So please do
Uh,
fast. Time is short.
yeah. Does lower pressure ratio refrigerant create any impact on our refrigeration cycle? Yes, lower pressure refrigerant will have lower heat of vaporization. So your flow rate will increase, and that you have to account in your heat exchanger design and compressor selection. Okay. Sir, will you help explain temperature glide concept? I explained in the slides, and if you want to get more insight, please look into the literature. Even then, if you're not comfortable, then please contact me. Which refrigerant have high heat absorbing capacity? There are a lot of other. There are a lot of refrigerant which you can compare and see which has the absorbing capacity, but it typically depends on the pressure, at which pressure you are referencing for absorbing capacity. Okay, is it the low temperature or the high temperature? So there are, you have to make a list of refrigerant and you have to look at that. It is very difficult for me to remember the name of the refrigerant at the moment. Which TR range is dominant in supermarkets? Oh yeah, that's a very good question. So typically 15 to 5 to 15 tons is a small size supermarket. 30 to 50 tons is a mid-size supermarket, and anything above 80 to 150 tons is a big size supermarket, and above 150 tons is a hypermarket. Okay, typically found in US and other parts. Is there any way to deal with the toxic refrigerants? No, you just have to mitigate the effect of toxicity. Like, if, for example, the ammonia systems where we use ammonia, you have very high ventilations, so that if the ammonia leaks, it straightly goes to environment without causing damage to the person. So there is only way to deal with toxic is to have good mitigations in the event of leakage. Research area where one can go through HVAC. There are a lot of research areas, like you can go in the development of heat exchangers, compressors, refrigerant development. You can go into the life cycle climate, LCA of that. LCA is life cycle assessment. You can go in the environmental assessment. There are a lot of things which you can research. Just Google it, you will find it. So the power consumption of the system depends on the selection of refrigerant. Yes, it is. It is very much dependent on the system, and I have explained in the slide. No question. It was wonderful presentation. Thanks a lot. Thanks a lot for this comment. I'm very grateful to you, sir, for valuable information. Excellent example at your field. Thank you once again. Thanks a lot. As the zero value of that is high, then why start to use it? There are other options which will be lower than okay. See, the environmental rules are decided now, and they have certain ways of phase out. It is not that from tomorrow you have to cut off the high durable refrigerants. So definitely there is some phase out rules, and that you can Google in the internet and you can find out. There are typically two different rule sets for developing countries and for developed countries. Okay, and it is also divided in the applications. So for the air conditioning application where R32 is used, there is no such regulation as such where we cannot use R32. It is widely used refrigerant and very efficient refrigerant. Okay, how risky it is to go for hydrocarbon refrigerant? It is very risky to go with hydrocarbon refrigerant. But if you have a low charge systems and good mitigation strategies, then yeah, that can be used. But yeah, it is risky overall. Look forward the mail ID of Purohit sir. It's good talk. Okay, thanks sir. I'll share my ID. Can you refer some material textbook to give an initiative understanding of subject? Very good. I will strongly recommend to see the the X-ray standards. First of all, if you can manage those, because they have lot of information, the X-ray handbooks, the X-ray journal, and then you can have some textbooks like CP Aroda from the Indian author. That's a very good book. And you can also go to NPTEL, which is a very good platform to understand. You have there is a very good professor from IIT Kharagpur, Professor Ram Gopal Madali, which happens to be my PhD external for my thesis. He is expert in refrigeration, and he has delivered a very good lecture series, video series on refrigeration and understanding the know-how about them. And most of my slides are influenced from those learnings. So you can also go and see that. Okay, thanks. Okay, sir.
Thank you, sir, for the wonderful session. Now I invite Sandeep Goyal, Program Chair of Jodhpur Subchapter, to acknowledge.
Okay, thank you, sir.
Am I audible, sir?
Yes, sir, you are audible.
Okay. Good evening, everyone. It's a great opportunity for me to give vote of thanks to Dr. Nilesh Purohit, sir, for the excellent presentation on refrigerants. I must say that you left no stone unturned, and thank you so much on the behalf of Jodhpur Subchapter and JIET student chapters. Thank you so much, sir.
Thanks, sir.